if you guys know me, you probably know me more as a computer vision person than a medical imaging person. So you might ask, why am I here? It turns out that us at Facebook AI Research was something that we're increasingly getting interested in is medical imaging. And this is one of the reasons why I was really excited to come here today, is to kind of get to see you guys, get to meet what's going on, get a better sense of the field, that sort of thing. And I'm really excited for the talks that are coming up. So if you look at my history, I've been doing computer vision for, a long time. Maybe 20 or 30 years now I'm thinking about it. It's kind of embarrassing. So I'm definitely from the dark ages. I've recently come to light in the last 5 years, I assume with most of you. My background is in stereo vision, it's in computational photography, it's in object recognition, it's in deep learning, it's in language plus vision, more recently it's reinforcement learning and all sorts of other things that have nothing to do with computer vision. So basically all over the place. But one of the things I like to do is I like to go back in time. I like to analyze how the field of computer vision has evolved and think about why are we where we are? How do we get to this place? And it's really interesting when you kind of look back and you say, OK, this is the paper that was here, and it was completely wrong. We only learned that 5 years after it was published, but it got us to this place here. And I think what's interesting, and what I want to do today in talking about things that happened before deep learning, and tomorrow when we talk about things that are with deep learning, is to kind of discover that. Talk about how the history evolved. Talk about what made the algorithms important and how they intertwined with each other. I think it's pretty rare that we get to see all these things kind of thrown together in one place. So before I start, I want to get a sense for you guys. So how many of you would consider yourselves like medical imaging students, researchers, that sort of thing? OK. How many of you would consider yourselves computer vision people that are kind of interested in medical imaging? OK, that's a good portion. And how many of you don't even really know what computer vision is, but you're medical people? All right. That's good. That means we can go a little bit faster. I wanted to get a sense for how much people knew about computer vision. How many of you know what SIFT is? SIFT? All right, that's not bad. Viola Jones? OK, a little bit less. What's another good one? Okay, and then I guess everybody knows what a CNN is, right? See, now you'll be embarrassed if you don't raise your hand. All right. So, OK, good. Let's start off. So the point of this series is how do we get here? Where are we going? Get a better understanding. And like I said, today we're only going to touch on deep learning. We're going to be talking about everything else, which is actually most of computer vision. So the thing I really want to emphasize, though, are the algorithms, why they worked, and why they failed. I'm not going to get into what boosting is, what an SVM classifier is, all those sort of things. There's other people who are going to be giving lectures on some of that. I'm not going to get into, again, the deep learning, obviously, but I'm going to talk about it from a computer vision perspective. So where did it all start? Well, obviously, it had to start after, computers and all this, the technology was feasible. And really the starting point, and I think a lot of people look at the starting point of computer vision right around 1966. And this is a time when Marvin Minsky, famous professor at MIT, went to one of his students, it was probably June, May, and said, I have an awesome summer project for you. I want you to take a television camera, get it? Attach it to a computer, and get the machine to describe what it sees. Think about that, right? 1966. Think about how much compute power there was. Think about how much respect there was for computer vision at this point. Not very much. You're going to solve it in 3 months with hardly any compute, right? So what do you think happened? Obviously failed, all right? I think they didn't even get the computer, the television camera even attached to the computer properly, because that's even a hard work of it, in and of itself. So if we look at now, you go 2 years into the future, and you say, OK, now what were people thinking about computer vision after they started looking at it? They started looking at things like this. It's like these simple problems that drove them crazy. So you look at this C right here in the middle. The amount of difference between that C and that C and that O is exactly the same. The number of X's stays the same that changed, right? But the point they're making in the paper here is that one of the permutations makes a big difference to us, and the other one makes very little. And they're like, how do we solve this? They're like, poof. It was hard to figure out. These are the type of problems that they were, just imagine if you're just getting into computer vision, you're just starting to explore the problems and what is hard about the field. This is the type of thing that you run into. Now, let's fast forward 5 years. How many of you know Takeo Kanade? Lucas Kanade, the paper? Tomas Kanade? All right, nobody knows. I think this is probably the earliest photo. I think this is Takeo Kanade right here, a picture of him in 1973 as a graduate student. One thing I want you to notice is that this is his thesis title, Picture Processing System by Computer Complex and Recognition of Human Faces. What's interesting is the first half of this title, Picture Processing System, literally that is what his thesis was. Is how do you take an image that we took with a film camera and get it into the computer? That was half of his thesis, just to get that part of it. And then once he did that, he's like, great, now I can start studying recognition of human faces. Right? And one thing that was interesting is not too surprising, when computer vision first started out, it was looking at digits. It was looking at simple, shapes and that sort of thing. And one quote from his paper is, it might be considered that recognition of faces or other natural scenes would be only a little bit more complex than characters. But actually, completely new aspects appear. And this was pretty enlightening. This was the computer vision field coming to grips with the fact that it wasn't simple, right? That you couldn't just solve this one niche problem, like how to recognize C's from O's, and that's just going to naturally transfer over to faces. And they're like, oh man, this is tough. And I think 20 years from when Takeo wrote this, he was talking to me, and he's like, recognizing chairs. He's like, we are never going to recognize chairs. Do you know how hard chairs are? All right, so let's all of us go back to 1970. Pretend you're Takeo's graduate student, and you want to recognize a face. How would you recognize a face? Anybody have an idea? How would you recognize a face? Anybody? Head detection? Oh, edge detection. Edge detection is a good one. Any other ideas? That gives you the underlying features. Another idea, yep. Key points. Immediately, Takeo would be like, I have no idea what a key point is. Edges, maybe. Any other ideas? What's that? Oh, eigen. Takeo probably knows what an eigen. Yeah. That's an interesting one, maybe. Histogram? What's that? I can't hear. Oh, skin color. That's a great one, except for one thing. It's 1970. Any other ideas? Face templates, getting closer. So let's say you want to recognize a face. You can have a face template, but then what is a face template made of? Yeah, there you go. How are you going to recognize a face? Well, let's break it down into the parts. Let's recognize the eyes. Let's recognize the nose. Let's recognize the mouth, right? Of course, that's how you recognize a face. So this is exactly the same insight that those folks in 1970 had, and they said, okay, I'm going to train an eye detector, a mouth detector, and a nose detector. Fantastic. Now that I have these parts, what do I have to do? Part model. What do you mean by part model? Is this a face over here? Is that a face? Yes. So what's the difference between this face and that face? Yeah, it's how the different parts kind of interact with each other, right? But it's not fixed. I mean, this face here looks a little bit more like a face, that face up there, but it's still a face, right? It's just like moved a little bit. So what you then do is you take the parts and you say, which parts kind of have that face configuration? And then voila, you have your face detector. Now there is some evidence within the literature that humans also kind of have these kind of part detectors. When we think about things as parts and we kind of put them together. How many people have seen this this before. All right. Do you see any difference between this one and this one? It's not that much of a difference, right? Now what I'm going to do is I'm going to take these faces and I'm going to flip them by 180 degrees. Let's go back and forth again. That to that. It's dramatically different, right? So there's something weird going on inside of our heads too. We're processing the underlying parts differently than we are processing the whole. And it's kind of interesting. Now exactly how that happens, I don't know, but it's still kind of interesting. So all of these intuitions came together in 1973 for this really seminal paper called The Representation and Matching of Pictorial Structures. And this image says it all. And if you've been in the computer vision field at all, you probably have seen this image, and you might not know where it came from, but it's this paper. And the idea, which it communicates really well, is you have these different parts, which is exactly what we just talked about, and they're kind of attached to each other by springs, and they can move around a little bit, but you kind of need this vague shape, right? And this worked awesome. It really did. So they took the data set, fantastic data set. You can even see the 70 hairstyles of the pictures of the people. And they, I think, got like 95% accuracy. Just nailed it, solved it. Face recognition, bam, solved, done. Not only that, they solved it with noise. It's pretty sweet. Now, imagine you're, 1973, you have to review the paper. You want to know where the eyes, mouth, and nose are. They literally had things like this in the paper where you had to go like 27, 20, like 20, 27. Okay, that's where the nose is. It's amazing what, how much, hoops you had to jump through to publish your paper back then. But they did a really good job. And I think the data set had a huge number of images in it. I think it was at least 15, maybe 20. But it was a really impressive work. This is one of the first papers that really recognized faces in the wild with real images. All right, that was 73. Something happened in the late 70s. Anybody remember what happened in the late 70s? Early 80s? It's really important right now for where we are. Neural networks, nope, too fast, actually they happened a little bit, but let's not worry about that. AI winter, the AI winter occurred. So this is the period where, our field, the AI field, because you could call it back AI, you could call it AI then. Basically, everybody was overpromising, everybody was super excited, everything got heated up, and then because nothing happened, because it didn't really work, right? And I think the whole field began to realize, okay, this is much harder than we thought. We got these faces, we got these images, but people were getting frustrated, funding began to dry up, and then what do you do when that happens? You curl back in. You say, okay, let's go back. Let's go back to the basics. So somebody, when they said, how would you recognize faces? Somebody mentioned edge detection, right? So we had the AI winter, early 1980s, and people went back to basics. They said, okay, at the end of the day, we want to recognize faces. We want to recognize chairs. We want to recognize cars. We want to recognize, and there was actually work done in medical imaging back then as well. And people were recognizing the same applications we do today as the important ones, but they were just getting frustrated because they weren't working. So they said, okay, let's go back and study the basics. So edge detection, finding corners. What I love about this image is corner detection. What's easier than detecting corners? Nothing. It's like missing corners here, here, up there, up there. Have many of you worked on low-level image processing and detecting corners and how incredibly frustrating even these simple tasks are? Yeah. You're like, I can't believe it didn't get it. What's going on? You look at an image like this, and you really get respect for it. Yeah, I got a lot of the corners, but it missed some as well. The other thing that was kind of cool about the 1980s was they took a very scientific view of computer vision. There's a lot of debate about what does it mean to group things together, like the Gestalt principles, like disease. We have different properties of lines, like closure, similarity, proximity, symmetry. There was a lot of great debates about, how do you represent an object? There's two main camps. One was we represent an object in our head as 3D shapes, such as these. These are called geons, where you have a limb that's 2 cylinders, and then you can have a hierarchical view like this, and break it down into these cylinders until you get to your fingers. I love the bird here. You can have these kind of three-dimensional and models in your head, or maybe it's you have a 2D image of an object, and then you kind of rotate it a little bit, you take another 2D image. So it's kind of a view-based representation of the objects. And there's many good debates going back and forth which one's better. Now, this fueled good papers, edutection, a lot of good papers during the mid-'80s. It was fun stuff. Did it get anywhere? We got canny edutection. We got Harris corner detectors. But not too much. And we were able to detect, I think, wrenches moving along like a machine assembly line. That was kind of cool. To detect whether the wrench was like done properly or not, that sort of thing. But something changed in the late '80s. And you kind of say goodbye science. So what do you think changed? Well, something began to work. And what was that something? Digits. So you got to think, it was 1970, 1960, we started looking at digits. It was only, 20 years later? They were like, figured it out. We figured out how to detect digits. And how did we figure that? Who figured that out? Jan did with his LeCun detector, but basically, as probably almost all of you know, if you have an image, you can take filters, you run them across the image, like so. Nice convolutional way, that's why it's called a CNN. Oh. And then you get a filter response, you shrink that down, which you generally think of as pooling, and then you repeat that a whole bunch of times, blah, 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 and you have a fully connected layer here, and we'll talk more about this tomorrow, and I think Renee has a lecture later today on the basics of deep learning, so you'll learn more about that then, so I'm not going to go into details now. But then you get a handwritten digit recognizer. And this really worked. And didn't just kind of work. This is what was amazing about it. There's like academic work. Like it worked academically, which means I could publish a paper on it. I could find a data set academically that convinced my reviewers that this actually worked, or kind of worked. It got about 80% correct. You know, that's like ideal when you publish a paper. It means that there's room to improve, but like you'd still do good. But this actually worked. Right? This, you could take this out. The US Postal Service could take this, apply it to handwritten digits on letters, and it worked. It might not seem that impressive right now, but when you're used to everything failing, this was awesome. People were excited. All right. So after something works, this is kind of where you saw a little bit of a shift in the computer vision field. Has anybody seen Jitendra Malik's lecture on computer vision online? A couple of you. The first sentence out of his mouth, and this actually struck me when he first said it, was computer vision is an engineering field. I hadn't really thought of it as an engineering field. I was, we're computer scientists, or probably many of us are computer scientists. You think of yourself as a scientist, but really it is an engineering field. We're trying to improve these metrics. A lot of this is engineering. And this is, I think, a big turning point in the field when we started thinking about things more from an engineering standpoint and just making things work better versus a scientific standpoint and trying to understand what is the fundamentals of representations, of things and how humans represent different objects. All right. So what also made convolutional neural networks really cool? Well, remember we go back to 1973 and we had Takeo, with this paper saying there's fundamentally different aspects than from characters to recognizing faces, right? Takeo said this, because the things that they applied to recognizing characters didn't work for recognizing faces, and they had to design completely different algorithms for doing that. So what was cool about CNNs? You could take the almost exact same algorithm and voila, it actually worked on faces too. That was pretty cool. Now, what's even cooler about this is this paper was co-authored by Takeo as well. So, it only took him 30 years now-ish, 25 years since when he was first talking about this to actually getting face detection to work in the wild. And there was some pre-processing that had to happen here. Obviously, the CNN here is kind of different, but the underlying principles and everything were roughly the same. Similar algorithms, similar techniques, and you were able to detect faces. So that was pretty cool. So at this point, and this is mid-90s when a lot of this work is happening, you think there'd be a lot of excitement, which there was, and you think like, man, okay, this is where things are going to take off. But then something happened, as it often happens in the field, is we make this huge advance, everything's moving really great, and then suddenly we start to plateau. And in this case, we plateaued around being able to recognize faces and digits. We started looking at more complex categories. We'll go back to chairs, that sort of thing. It didn't work. And we're like, we couldn't figure out why. Tomorrow, we'll talk about this. When we get to 2012 tomorrow, we'll discuss what happened. How do we start that slope back up? How do we start recognizing things and do a good job again? Right? Did anybody know what the quote is on deep learning? Or actually, it wasn't called deep learning back then, but neural networks back in the 90s? What do people say about neural networks in the 90s? The second best way to do everything. That's what everybody used boosting, you use SVMs, you use other things, but neural networks is like, eh. And when you publish a paper, if you use neural networks, the reviewers would ask you, why did you use neural networks? Why didn't you use something else? To kind of give you an idea of how the field felt about neural networks back then. All right. So before I go on, just a little side note. For those who maybe aren't quite as familiar with computer vision, there is a distinction between classification and detection. Many of us talk about image recognition, and then there's kind of two subcategories, classification and detection. Classification, when I say that, it means I have an image, just tell me whether there is a dog in it or not. And then when you have detection, such as this, you actually want to detect where the dog is in the image. It might be multiple dogs, it might be no dogs, and then if there is a dog, draw a bounding box around it. That's detection. And as you might imagine, this task is much harder than this task, because if you solve this, you can solve this, but not vice versa. All right? So the year is 2000, roughly. Now imagine, take yourself back to the year 2000. Probably most of you weren't, well, no, you probably were alive then, but you're probably wee little ones in 2000, I would imagine, at least many of you. So imagine yourself in 2000. I think this is the Pentium time frame. Does anybody even remember what computers? Oh, this is like the first those cute little Macs came out, if I remember correctly. Is that right? I don't know. The processing wasn't that advanced. But imagine you're Paul Viola, and you're standing on stage. Computer vision, kind of works. You don't really see, computers aren't that fast. And he pulls out a camera. And you're at a conference, and you're at the biggest computer vision conference there is, right? So how many people are you standing in front of at this point? Probably about the same number of people as are here, a few hundred. This is before the days when, deep learning became popular and there were thousands of people out there. But, a few hundred people, you take out your camera, you show it up here, and up on the screen, you see a face detector running in real time. At this point in 2000, seeing real-time face detection really blew people away. They were like, wow, because before this, we kind of knew that face detection was working, we knew the character recognition was kind of working, but to see these things work in real time on kind of a standardish machine was really eye-opening to the field. People were really impressed by this. Now, how did this happen? And this is Viola Jones. People heard of Viola Jones face detector? Not too much? Maybe, okay, a little bit. This is what's in your cameras right now. You might not know it. You might look at that little face detector in your camera. You might think it's deep learning. It's not deep learning. It's Viola Jones face detector or some variant of that because it is so efficient. So why did this work? Well, we use something called boosting. It's a machine learning technique. I won't talk about that too much. Had a cascade classifier, which is essentially you look at you train like a simple classifier on a bounding box. And you say, is there kind of a face? Maybe is there a face? If it thinks, oh, there might be a face, then you apply another classifier, which is a little bit more computationally expensive. And if that one says, okay, I really think there is a face, then you apply your most expensive classifier to then determine whether, is there really a face there or not. And that way you can scan through all the boxes in the in the image, and look for every single face in a very fast and efficient manner. But one of the fundamental things that make this work was something called a Haar wavelet. A Haar wavelet is a feature. And this feature, which is what you train your classifiers on top of, if in CNN lingo, this is like your filters, that sort of thing, is simply a box, the sum of all the pixels in this box, minus the sum of all the pixels in this box. So it's just saying, is this box and this box, which one's brighter? Or which one's darker, right? Over this averaged area. And that's your Haar wavelet. Why were Haar wavelets, why did they use Haar wavelets, do you think? efficiency. You can compute these super quick. Does anybody know what an integral image is? All right. How many of you plan on interviewing for a computer vision job sometime in your career? All right. This is something you should know. The one time you will probably most likely to experience the question of what is an integral image is probably going to be that interview, just knowing like computer vision interview questions. So I will give you a quick briefing on what that is, and you'll be like, damn, I wish I would have remembered what Larry told me back 2 years ago. All right, integral image. Let's say you have a very simple task. All you want to do is find the sum of all the pixels in this box, and you got to do it super fast, constant time. How do you do it? Well, I'm not going to ask you because it's too hard. So the idea is really simple, is you pre-compute something called an integral image. An integral image is essentially what you do is you take for any box, is you store what the sum of all the pixels are to the upper left-hand corner. And you can imagine you compute this one first, and then you move to this one, and this one, and this one, and you keep basically just adding them up, and you go raster scan order, blah, 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 until you cover the whole image. And then down here, you get the sum of all the pixels in the entire image. So you can do that constant time as you go across. It basically takes order n in the number of pixels and compute that integral image. Once you have that pre-computed, you can very quickly compute the sum of any pixels or any box within the image. The idea is the following. You have A, B, C, D. These are the values in each of these boxes here. And you could take the sum of all, you take D, which is the sum of all the pixels here. So that's D. And you say, okay, well, this part here we don't want, so let's take out B. We don't want all the pixels here, so let's take out C. And then we took out this area here twice. So you need to add A back in. And that's equal to the sum of everything in here. Pretty cool, right? So that allows you to take the sum really quick, means you compute those hard wavelets super fast, constant time, and made everything really good. The next thing you might be thinking to yourself is, well, that is a really simple feature. Like we think about the features we have nowadays, with the CNNs, multiple layers, all these nonlinearities, like these very complex things that are going on. These features, you don't get simpler than these features. Why did they work? It doesn't make any sense. Why something this simple could do something as complex as face detection. Imagine yourself going back to 1970, 1960, and telling Takeo or Marvin Minsky, and they come up to you and say, I want you to build a face detector. Nobody here raised their hand and said, I know how to solve this problem. I'm going to take all of the pixels within this box, and I'm going to subtract it off all the pixels in this box. I want to do a bunch of those, and I'll train a classifier. I think that'll work. No. Everybody would have been like, no, that's never going to work. It's too easy, too simple. So why did this work? Why does a hard wavelet work? Anybody have any ideas? Because you can what? Oh, you can do plenty of them, yes. You can compute a lot of them. More likely you're going to hit upon one that's good. That's a good point. The face always has the same shape. Oh, the lighting. Yes. It's a great point. Where does light come from? Does it come from below? No. Does it come from above? Yes. Lighting is almost always coming from above, right? That's when you see the picture of somebody with a flashlight right underneath their head and they look really spooky because you never see somebody's face lit from underneath. So the lighting is always from above. That's awesome. People's faces, are they roughly the same 3D shape? Yes? So that's good. So they look pretty similar. Any other reasons why faces work well? Well, the other one is you take a bunch of faces, you kind of average them together. Like the structure, what the faces look like inside is all very similar, right? Like this northern Italian here, and you take the average of all the southern Italians. I can't really see a difference, to be honest with you. But apparently there is one. Maybe those from Italy here who have a better time at telling than I do. But if you look at it, the structures interior to the face, they're pretty much the same, right? There's a little bit of blurriness at the hair. We all have different hairstyles. The background obviously is very different. Maybe the jawline's a little bit different, that sort of thing. But the nose, the eyes, the mouth, the things that we were talking about before are very consistent, like that. So when you take a hard wavelet, it turns out that you can have a hard wavelet that looks like this one, very dark eyebrows, the eyes. You take the light, the too dark. These are really consistent patterns on faces. It works. That bridge of your nose always gets the light from above, which means it's brighter than everything else. And the hard wavelet picks up on this, and it detects the faces. This is why it works. Unintuitive, but it works. And again, I think you look at this from an engineering perspective, and you're like, wow, that's really freaking awesome. All right. So that's why it worked. Why did it fail? Why didn't it generalize? Let's take something very similar, but yet very different. A portrait of a face. Why were portraits of faces so much harder to detect than the frontal faces? Any ideas? Why is a portrait hard to detect? Not symmetric. We could build one for this face and then one for the face looking this way, and they did do that. Background's more important? Is that what you said? Why is background more important? Yeah, and why do we care about the background on a portrait? It's because what is the distinctive feature of a face when you're looking at it from the side? It's this line, right? That's what makes it a face. And that face is part background and part foreground. And that background can get bright, it can get dark, it can be all sorts of different things, right? So if we look at this hard wavelets, they're no longer repeatable. We don't have that consistent lighting that we were talking about before. We don't have that consistent 3D shape that we were talking about before, because the background can be anything. And the hard wavelets didn't work as well. Kind of a downer. And you think about other shapes, other objects like mugs, what makes a mug a mug? Well, it's that shape. It's that shape again, of a mug shape. But then here, neither the interior is consistent because you can get all sorts of different, types of mugs, and the background is obviously going to change as well. So you take something like a hard wavelet, is this going to face plant on something like this? All right. So what was kind of cool about this was faces worked. We are humans, we care about faces. So it showed us some good progress, made sure that our field wasn't going to die, always a good thing. But of course, we hit the dead end. We're like, man, shoot. I wish we could have done better. All right. So that was 2001. Let's go back in time. Let's just go back a couple years. Now, if you think about what we just learned, was that these very simple features did a great job on faces, which are fundamentally a very simple thing to detect, right? But what do we want to do? We don't want to just detect faces. We want to be able to detect, chairs. We want to be able to detect cars, bicycles, all sorts of other things. And if we want to detect these more complex objects that have this interaction with the background, what are we going to need to do? Well, we're going to need better features. And if you're in 2000 or 1999, if you're not worried about the world ending in the year 2000, people really did worry about that, by the way. You were thinking about computation because you didn't have that much compute power. If you don't have that much compute power and you want to use more expensive features, you're like, shoot, what are we going to do? Well, what if we don't do that sliding window approach? Like the way that Viola Jones worked, you look, is there a face there? Yes, no, no. Is there a face there? Yes, no, no. Yes. No, 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 no. Yes. No, 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 no. Yes. No, 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 no. And you could do that because it was really efficient. But if your features take forever to compute, you're not going to be able to do this sweeping window back and forth. So you got to be really careful about where you compute your features in the image. So the idea was, so next slide, sorry. The idea was, what if you only compute features where people fixate, where we think there's actually an object? We as humans, we don't sit there and, if I'm looking for a face, I'm not going like this, and scanning the entire image like this. It'd be very inefficient, right? You take your eyes, you're kind of flying all over the place, and you kind of fixate on a person's face, and you're like, there's a face. Why don't we do it just the same way that humans do it? So why don't we compute fixation points? So I want everybody take a moment now and just try this exercise. Look at this shape here and trace the trace the outline of that object with your eyes. Just go around now. Okay, did everybody trace the outline of that object with their eyes? When you did that, did it feel like your eyes are moving smoothly as you're moving along the outside of the object? It should. It really feels like you're just going continuously along the outline of the object. Do the same thing on this one. All right, so you just took your eyes, you slowly went around. Maybe you started up here, and your eyes slowly went around, and it felt like you had this nice smooth motion as you were looking around this object. In reality, that's actually not what's happening. In reality, your fixation points look more like this. So these red dots are where the eyes are fixating, and your eyes are kind of jumping from one spot to the next. But somehow our brains kind of fool us into thinking we're looking at this kind of continuous movement in our eyes. And that's not the only thing that's cool. This is what the fixation pattern looks like on the larger version of it. But if you look at the smaller version and you look at the fixation points, is that the fixation points are actually quite similar to each other, even though we have different scales of the objects. So you can see like this fixation point here is kind of similar to this one similar to this one here similar to this one. Maybe they changed a little bit. This is just one subject, me. So obviously there's a little bit of variability, but you can even see it if you go a little bit smaller. So the thinking here is, well, humans, we don't look at the whole image again. We look at these small number of points. Can we find these small number of points and just evaluate the image at those same points? All right? This makes a lot of sense. And if you're in the late 90s, early 2000s, you want to make things that are computationally more efficient, this makes a lot of sense. Of course, at the same time, there's a lot of debate. These fixation points top down, bottom up, blah, blah, blah. Who cares? Let's not worry about that. Let's just assume the bottom up for now. All right? The truth is that there actually are a lot top down. They're also a little bit bottom up, but let's ignore that fact. All right, so SIFT. How many people have heard of SIFT? Awesome. How many people, again, sorry to bring up the job interview type of thing, if I sat down and you said, can you describe to me SIFT in detail, how many people would feel comfortable doing that? All right, not so many. All right, SIFT is really awesome. So scale invariant feature transform. So no more sliding windows. We want these better features by using interest points. Computing the SIFT descriptor is going to be a lot more computationally complex, but it's OK because we're only going to do it at a small number of points in the image. So let's first talk about how we actually find the locations where we want to compute the features. So there's 2 points to that. 2 things in SIFT. One is the interest point, the locations, and the other one is the descriptor. Right? Interest points, think like that's a location in the image. I want to sample the features, and then the descriptor is how we represent the pixels themselves. So SIFT used something called DOG, which is an acronym for difference of Gaussians. So difference of Gaussians, as the name might imply, is when you take an image, you blur it with a sharp Gaussian like this one. You take the same image, you blur it with a Gaussian that looks like this one, which is a little bit bigger. You subtract the two, and then you get something that looks like this hat-shaped thing, which is actually really close to something called the Laplacian of a Gaussian. But it turns out that computing the difference of Gaussian is much more computationally efficient, so that's what people did. And then if you look at a 2D filter response, it looks like this. And if you ran this filter across your image, what do you think it would spike at? Where do you think it would spike? What is it going to detect? Is it going to be like the Harris corner detector that detects corners? No. What is this going to detect? What's that? Edges? Nope. What's that? Yes. It's going to detect, well, where the intensity is extreme, but basically it's going to detect bright blobs or dark blobs. Right? If you have a big bright area in the image, this is going to respond really strong. If you have a really dark area in the image, it's going to be the inverse. It's going to be a really negative response. So really, when you think of difference of Gaussian, think of it as a bright and dark blob detector. That's all it is. But it's a really efficient way of doing it. So the way that you actually compute it is you have an image like this one, you progressively blur the images like this, and you get a whole stack of images blurred, and then you just subtract off neighboring ones, and this is the difference, and this is the absolute value of the difference, and then you just look for peaks in these images. And when I say look for peaks, I don't mean just in a 2D image here, but if you look at let's say a peak here, you make sure that it's a peak in this one and this one as well. So it's a 3D peak. So it's both in scale space and in XY space. Right? You find those peaks, and those are your interest points. And that's what you see here. So the size of the circle shows you where in scale space you were. So like these little bitty circles are like if you were way up there and you detected the peaks in the top one. And then if you detect peaks down here, those are these kind of big circles here. And you kind of see how this is kind of like a dark blob. Maybe this is a brighter blob. You think it would detect this bright blob here. Maybe it's higher in scale. I don't know. Anybody who's played around with interest points at any point knows how flaky they are. And they're not as reliable as you might expect. But this is what they look like. Now, we have our interest points. And let's say that we have, where's the peak? Let's say we have this peak here. Can you guys see that? Yeah, a little bit. I'll make it bigger. Let's say you find a peak right here. Now what you want to do is you want to compute your descriptor. This peak tells you an XY position, which is great. Where it is in this hierarchy here tells you its size. So something down here is going to be a bigger interest point. Something up there is going to be a smaller one. And then you can do things for orientation as well, but I'm not going to talk about that. But what people then did is they said, OK, then I'm going to take that point right there, which corresponds to this patch right here, and then I'm going to sample this patch in this image. Right? If I found a peak over here, like up here, then I would sample, like, let's say, a nice little small patch in that image up there. All right? Super simple. Why did we sample patches here for this one and that patch up there for that one? Well, those are small patches we want high resolution. These are the big patches we need lower resolution. You want to sample in a way that doesn't alias. For those who have some image processing background, that's the way you want to do it. All right? What's important here is like when David Lowe was doing this, he did it right. He really thought about how to sample the image properly, how to build this pyramid properly, how to sample this in a way that you don't have aliasing artifacts. These are critical design decisions. The other thing is, let's say you have this red box right here, is the descriptor you want to sample. This is your underlying image. These did things like these small little details, but these small little details made a big difference. You want to sample this position here, and what you had to do is you had to sample it from 4 other positions that are around it, and then you have to use bilinear sampling to do that. I can't even spell. I'm so tired. There we go. I got my first good night's sleep last night, in case it's not obvious. All right. But basically, he sampled this correctly. And you think, OK, why am I telling you this? I'm diving into the weeds. And it shouldn't make any sense right now. But wait till tomorrow, and this will pay off. You understand why I'm talking about these things. All right. So you sample these pixels properly, and then from your image, you grab out a patch. It looks like this. You did a really good job of making sure you're sampling everything just right, and then you compute your descriptor. And what is your descriptor? Well, you take your image patch here, you compute the gradients, and you compute the magnitudes, and this is basically showing you the orientations of the edges and the magnitudes. You weight them by the blue circle here shows a Gaussian, which means you want to weight the gradients which are closer to the center more than the ones that are farther away, because the ones on the edge are probably more likely to be noisy. The ones in the middle are supposed to be more reliable. And then you take this, and then you take all of the gradients within this area here, and you sum them together. You basically create a histogram. This seem familiar to anybody? It's very similar to, yep? What's that? Oh, okay. So, yes. So, this looks kind of like a pooling operation for those of you familiar with CNNs, right? Where you just take all the gradients, you kind of pull them together, and you get a histogram of those. And then you just take all of these, and in practice, this wasn't 2 by 2, it was actually 4 by 4, and each one of these had 8. So what you would have is a 4 by 4 times 8 vector. So that's 128, if I do my math correctly. I think that's right. And you put them into a histogram, and you normalize it, so that way they all sum to 1. And then you get a descriptor that looks like this. There is still one remaining problem. So now you're David Lowe. You're designing this thing. You've been working on it for years. The year is, actually, when he was working on this, it's probably 97, 98. Right? Actually, it's probably 97. So 96, 97 when he's working on this. Any idea at all what would be a problem with this histogram? Projection? Rotation. So one thing I didn't mention, I totally skimmed over, but when you sample the patch, you actually look for the orientation which has the highest magnitude, and then you rotate that entire patch so that way it aligns with that orientation of highest magnitude. So there was additional noise added into that. I brushed over that, but then that would be an issue. But any other ideas? What's that? Illumination? That was the beauty of the normalization, if you think about it. Because when you compute these gradients, you could have some patches which had very little. Again, you're computing gradients, so you don't have to worry about the offset, the brightness or darkness of the image. But now you have the magnitude of the edges within this patch. So some image patches, these errors will be really small if there's not much contrast, and then some of them will be really big if there's a lot of contrast. But the nice thing is if we normalize that so they all sum to 1, then you get that nice figure like this. So the remaining problem is actually something that's really not obvious. The problem is that most image patches will have one set of gradients that are dominating in magnitude. You take a random patch from the world, and there'll be a lot of edges like all vertical, or maybe all horizontal, or all like in some other direction. So you get a descriptor that looks something like this, where you get a bunch of small little gradients, and then you get like a spike and a bunch of small ones. So why is this a problem? Well, this is a problem because we want these features to be unique, discriminative. And if there's a ton of other patches which have like a spike here and a bunch of like random noise here, they're not going to be that discriminative. Basically, there's 128 dimensional, which means you roughly have 128 unique features. Or maybe if you're lucky, 128 squared. Because you maybe get a lot of patches that have a lot of gradients like this and a lot of gradients like that. And you kind of like rotate it like that. So what did David Lowe do? He did something called truncated normalization. So he took all of the values in the histogram. He said anything that's above 0.2, not 0.3, not 0.1, 0.2, it's very important. Above 0.2, he cut it off and then renormalized. And what did that do? It took all of this kind of things that used to be kind of like noise and made them all equal. And then your descriptor now is much more unique. Pretty cool. So you have these descriptors that are repeatable, they're very unique, and you can use them for all sorts of fun applications. Now, why did I just step you through all of this stuff that I just mentioned with SIFT? It seems like a lot of details. If you read the paper, the first time you read it, you won't understand everything. It's kind of like the deformable parts model, or like the histogram-oriented gradients, which I'll talk about later. All of them are really tough because it takes you a while to fully grasp everything that's in the paper. If you were a reviewer of this paper in 1998, and you looked at this, you would say, this is an amazing set of hacks. Like, why are you doing all this? You have to do truncated normalization? What the, this doesn't make any sense. You have to do this Gaussian weighting. Like, this just seems like, this is like overly engineered. Like, come on, reject. And that's exactly what happened in 1998. David Lowe submitted this paper. They looked at it. They're like, oh, you want me to publish this long list of hacks that you made to do something called interest points, which who even cares about interest points anyway? I'm not going to accept this paper. Rejected. 1998, on the other hand, he got the paper accepted. So that was cool. David Lowe, he's persistent. He's been around the computer vision field for a while, so he understood what rejection was like. But even after that, in 1999, when it was accepted, it didn't really catch on. So anybody who was, I'm not sure, probably 3 of you are around in this age, in the year 2000, 2001, 2002. And again, like SIFT, we think about it today, it's super popular, everybody talks about it, but back then it's still like, like nobody really knew about it. So what did David do? When you have a long series of hacks and everybody's like, man, there's no way I'm going to be able to reproduce this, he released the code. That was huge. What else did David do? He actually went around and he gave talks. And I remember sitting in an audience of one of his talks, and he took a picture of like something, and then he like took another picture of it, and he could show that you could align it like this. And 20 years later, it doesn't look impressive, but back then you're like, whoa, I can't believe this actually works. And he went around talking about it and popularizing it. And people were like, wow, this actually really works. This has practical value. And he was able to show. And this is basically a 2004 paper, which is what most people cite. You see the citations start taking off. But it took a while for the research field to catch up to it, to really appreciate this work. So just because your paper is not recognized in the first year, the second year, the third year, the fourth year, the fifth year, it might get recognized later. It would probably be forgotten, to be honest with you. But there's a chance it could still be remembered. Or if you're young, it might be 20 years later. But that's just how it is. If you look at Viola Jones, this is the citations for Viola Jones. It looks more like this. So it kind of, and this pops up. Because this is something, when he did it, like basically everybody on it is like, whoa, I can't believe how awesome that is. And it really took off, right? There's a lot of different papers, a lot of different types, So it's just like important to know that, there's a lot of different ways that papers can grow. Don't get frustrated. If you do good stuff, hopefully it'll get recognized. All right, so this is the type of thing that he was showing. You have a box like this, and you can register it with that. If you were around, CDs were really cool back then. So I'm not sure if everybody remembers David Nister on stage doing air guitar, picking up a CD and then being able to recognize it. Again, probably none of you were actually there to see that, but this is like in 03 or 04 or 05, something like that. But that was really cool. Now, of course, CDs are no longer popular. Nobody cares about that anymore, but that's all right. The other thing that was really big is panorama stitching. This really enabled panorama. It's like another application that people saw a really good use case for this sort of thing, is how to take multiple images and stitch them together to get big panoramas. We take this for granted right now. It's on every single camera, but this is a really big deal in 04. Like nobody had been able to do panorama stitching before that. All right. Why did it fail though? Why did this idea of using interest points and more complex features fail? Why didn't this finally recognize chairs? So in order to understand this, let's look at another paper. 2003, the Constellation, Object Class Recognition by Unsupervised Scale Invariant Learning, which looked again at the constellation model. This is by Rob Fergus. And I believe this paper won the Test of Time award as well 10 years later. So the idea was, you have something like motorcycles, just parts. They're similar to each other. So this rear wheel here maps that rear wheel, the front wheel maps that front wheel. This is exactly the same conversation we had about 20 minutes ago about faces, but it applies to motorcycles as well. And you can basically group the parts, put springs between them, literally. This is exactly the same, like Rob Fergus and the rest of them were citing the pictorial structures paper that I mentioned about 1973 a lot when they were talking about this work. But then, it looks exactly the same, but now we're doing it not just for faces, but we're doing it for motorcycles, we're doing it for back of cars. He did it for faces as well, and a couple other categories. But then the question is, how do you find these parts? So basically, we just took the problem and said, instead of recognizing motorcycles, we're going to make the problem easier. Now all you have to do is recognize the back wheel of a motorcycle. But that's hard. And they had the same thought that we had talked about before. So they were like, we want to use more complex features because they're hard to recognize. So let's use interest points to find the places we should, evaluate. And then we use descriptors to then say whether this is a back wheel of a car or not. So you use interest points, and this is what the interest points look like on the motorcycle. And then you can pull out different parts. Conceptually, it was really cool. Like this is an awesome paper. The other thing that made this paper awesome was look at this image. It's a real image of a real motorcycle. Back then, you didn't really take it for granted. I mean, other than faces, you didn't really see real images quite as much, where things actually worked. But why does this fail? interest points. So SIFT used dog, right? Difference of gradients, which are basically black blobs, or white blobs in an image. Or you can think Harris corners, which try to find those corners, which we mentioned earlier. Even that super easy image were kind of noisy. There are a lot of other interest points out there as well. But if you look at the interest points detected, on this motorcycle, and interest points that are detected on this motorcycle, how many of them actually correspond with each other? Do any of them? Can you find one? I mean, this wheel here, this one here is kind of like, this interest point kind of, like that one there, which is that big wheel, kind of corresponds to this one, but I got the scale wrong, right? And then let's see. You think like this one that fired on the handlebars there's nothing here, so that didn't work. The tailpipe one here looks really nice, but then there's no one here. Maybe the back seat here, fired over the back seat, but this one here isn't really on the back seat. And you probably remember doing this back in the day. Like, you're looking at these images, and you're like, why don't these interest points work? I probably spent a couple years of my career trying to design a new interest point, which actually fired repeatedly on images like these. And it just was futile. You just couldn't get it to work. It was really frustrating. You're banging your head into the wall a lot. All right. So this didn't work. So now you're thinking, if you're following along and still paying attention, you're probably thinking to yourself, OK, interest points don't fire reliably, so it doesn't work for that reason. But you just told me it works for motorcycles, faces, back of cars, all these sort of things. So how does this even work? How did this paper even get published if it doesn't work? Any guesses? It showed revolutionary results, but relied on a technology that doesn't fundamentally work. This is the data set. There's something called the Caltech 4 data set. I guess there was actually 6 categories in the paper, but this is the data set. And this is what passed for real images back in 2004. Anything peculiar about these motorcycles? Perfectly framed, all facing exactly the same direction. Same with airplanes. These faces are literally a graduate student walking around Caltech with a camera with the exact same flash, taking pictures of people's faces going tick, tick, tick. All the faces are roughly the same, all the same lighting. It worked pretty well. This was from a video of somebody following cars where they took a picture of all the back of the cars. Like, all the images were very similar to each other. And because all of them were very similar to each other, it means that the interest points kind of worked for these sort of images. You get away from this data set, totally failed. And even in the motorcycle one, there were a lot of motorcycles all on white backgrounds, which also make life easier. All right? So think about this a little bit. I'll talk about this a little bit tomorrow. But the philosophy back in the day here was find an algorithm, think of a cool algorithm, something that will work, and then find a data set in which that algorithm will work on. And try to find the hardest data set you think that algorithm will work on. Show it to the reviewers, cross your fingers, and hope it gets in. All right? All right. That's why interest points didn't work. So let's fast forward. Now we're in 2005. We're kind of getting into the modern era now. So histogram of oriented gradients. So at this point, this is Dalal and Triggs. Anybody know of Dalal and Triggs? That paper? Bill Triggs? Nah. Never mind. So basically, they wanted to detect pedestrians. So what makes pedestrians hard? Does this have all the properties that we were just talking about? Of things that are hard to do? So what makes this hard? Why is pedestrian detection a difficult task? Any ideas? Yep. Exactly. So you think about a pedestrian, we all wear different clothing, so the interior textures change. Not only that, the background in which the pedestrians are on changes a lot, right? So that means you have the interior texture and the exterior texture both change a lot. So this is like that mug example I talked about before. So this is like a really hard task at this point in history. So, and then we know that interest points don't work for this sort of thing. So they're like, okay, interest points, that was kind of cool, kind of fun, but for categories like this, we can't use interest points, let's throw them away. If you're not going to use interest points, what do you have to do? Sliding window. So you're going to go along your whole image and say, is there a person? Is there a person? Is there a person? No, 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 no. Yes. No, 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 no. Yes, yes, yes. No, 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 no. Like that. So pedestrians defined by their contours. Again, cluttered backgrounds, significant variance in texture. So interest points don't work. Going to sliding window. Put yourself back in 2005. You have a window like this one. You want to come up with a set of features which you think will be good to detect this pedestrian. What features do you use? What are the coolest features out there in 2005? Well, histogram of gradients, because you know the answer, but sift. Remember, we have sift, and you have the gradients like this. Well, let's just put sift descriptors all over the image. So they look like this. So basically, you're going to go histogram of orient and gradient. So basically, this is the histogram. These are the orient and gradients kind of pulled together, and you're going to create a big histogram out of all of these. Fantastic. So it's very similar to sift, but it's just dense. And instead of like sift, where you do interest points, you're going to be applying the sift feature descriptor densely across the entire image. But there's going to be a couple minor tweaks. So when you do sift, let's say now this is like your, this is your new histogram of orient and gradients descriptor. In sift, remember we did the normalization? So we would normalize, let's say this one and normalize this entire patch, so it's summed to 1. Well, if you do pedestrian detection, let's imagine that this is the upper part of the pedestrian. There's your head. You have the body like that, right? Is that some of these are going to be on the background, which are going to be who knows what that's going to be. Some of these are going to be kind of interior textures, which might be a little bit noisy as well. So when you normalize, this overall descriptor is not going to be very good if you normalize the entire thing. So they had one really cool idea. Well, there's a bunch of cool ideas, but this is one of the cooler ideas, which was, let's just do the normalization locally. So they did 4 normalizations, one with this patch with those 4, or those other 3, this one, and that one. And the cool thing is probably one of these, like this one, the normalization that you're doing is going to be all on the interior of the object. So it's going to be more repeatable. And what you want to do is if you have just some of the features in your descriptor which are going to be repeatable, which the classifier can use, you're going to have a better classifier. All right? So it's small, kind of subtle change, but this made a big difference in how well this worked. Yep. Oh, no. All right. So then you could take this is like an image. This is a visualization of the histogram of orient and gradients. This is the positive. We need to train an SVM classifier because that's what everybody uses, SVM classifiers. These are the positive weights and the negative. And you can see what it picked up on. It's kind of the silhouette of the pedestrian. And these are the not pedestrian lines. So basically, you don't expect a line kind of down the middle of me if there's a pedestrian there. All right? And this worked quite well for then. So compute hog features. You do this for every single bounding box, a linear SVM classifier, non-maximal expression. That was the algorithm. So I have 15 more minutes, right? I have 15 minutes? Good, good, good. All right. So why this worked? So because of that normalization that I was talking about, we could finally detect object boundaries fairly reliably. Hard negative mining was another one. When they trained the SVM classifier, they did a really good job of finding hard negatives, so that way the SVM classifier would be good as possible. And this is a big one. Computers are fast enough. This wouldn't have worked in the 90s. This took a lot of compute. But by this point, I think we're on Pentium 5s by now, Pentium 6s, I don't know. Whatever, the computers were fast enough at this point that you could run an algorithm like this. All right. Why it failed? So did this solve object recognition? No, obviously. But why did this fail? Yep. Oh, so one problem is for small people. How did this work? So I think when people got too small, You saw that that histogram of oriented gradients, it was quite high in resolution. And if you look at the data set that DeLongchamp used, the people in it were, I think 32 by 32 pixels at least. If you got smaller, then it wouldn't work. Any other ideas? So small people, and why do small people matter? Self-driving cars, right? That small person is going to be a big person in about 3 seconds, assuming you're going 60 miles an hour. Why else did this not work? Yeah. Can have what? Oh, pose, yes, exactly. That's what I was, yeah, exactly. So what makes pedestrians cool is pedestrians can kind of, they look like this. They kind of stand up like this. Did you have a, no, okay. They kind of stand like this, they walk like this. They all kind of look the same. You don't see pedestrians kind of like doing this too often, right? So if you look at basically your average edge contour of a pedestrian, it looks something like that. But, people don't always look like that. They're in different poses. So, this is kind of cool. First time we could detect stuff that, had interior texture, mainly detected on the this occlusion boundaries, but still didn't get to this articulated pose, this more complex objects such as these. All right. So recognizing this, everybody was really excited about this. I remember actually thinking in 2005 when I saw that paper, histogram of oriented gradients, I was like, it's okay. It only detects people, pedestrians. It's not that cool. Not realizing how cool it was going to be. But, the field was kind of excited about it because, again, it was another use case that actually kind of worked. Now, if you ran a person detector on an image like this, that's what you would get. Not very good, especially if you're used to looking at deep learning results nowadays. Now, if you look at this and you're a student and you're not looking at the title of the slide, and you're thinking to yourself, like, I can't believe you detected a person right here. This person doesn't make any sense. I know what I can do. I can use context, because there's no reason that a person should be here, or there should be a big person here. But given that scene, I know that there's only so many places in that image that people could actually exist. And if you do that, you get detections that look like that. And what they did is they said, okay, where is the vanishing, the horizon? And you can look at, where the ground plane is, and from that you can tell that people can be smaller up here, people can be bigger down here. And you can also look at the cars. So basically you do like car detection as well, and then basically say like a human has to be a relative size relative to that car. So that way you didn't get too many big discrepancies. So people should stand on the ground, and they should be roughly the same size as cars, and that reduces a lot of your false positives, and you can get a much better score. This is kind of cool. 2006, this was a big paper. A lot of people were excited about it. And the reason for it was because the first time that we started looking at contextual reasoning, looking at the relationships of objects to each other. All right. So why it worked, the world is not random, obviously. Contextual cues sometimes can be reliably found. Why this approach failed? Well, as you might imagine, it relied on finding the horizons. It relied on finding the cars, and car detection's just as hard as people detection. So there's basically noise in both. And when you take noise plus noise, sometimes you don't always get no noise. So you need more data, and it doesn't help with false negatives. So it helped with false positives, but if you didn't detect a person in the first place, it wasn't going to magically, find that person for you. All right. So let's go back to this problem here. Now let's imagine that you are, what year is it? Like 2006, 2007. And you wanted to not only be able to detect pedestrians, but you wanted to be able to detect people like these as well. What are you going to do? You're an enterprising graduate student. You want to come up with the next coolest paper. What's your best idea? What's that? Parts. Oh, bag of words. Bag of words, yes. You could use bag of words, because then you don't care about the spatial structure. So bag of words is basically you look at local features and you kind of classify them, but then you kind of throw away the spatial information. So the idea on these would be like, if I can find a box which has some arms in it, a head in it, maybe some feet in it, and they're all within a box, you'd say that's a human, and you don't care about where the relative locations are. That could work. Where that fails is if you have a bunch of people standing next to each other, then you get random parts of people everywhere, and you don't know which parts go to which people, and you get all sorts of random detections, and it's hard to pull apart. So what can you do? Yep. Try to find a 3D body model. That would be interesting. Unfortunately, so the idea was, can we get a 3D model of the body to say which configurations are actually feasible? And that would be kind of cool, but we're kind of in, it's 2006, 2007, we don't have a lot of data. That can be tough. We do what we did in 73, do what we do in 03, do what we did, many times in the computer vision field. You break things into parts. Again, so you have feet, heads, arms, that sort of thing, like this. So basically, you have a full body detector, you have different parts, and then you have a representation of how much those parts can move. So your head can move, a little bit like this, your arms can move a little bit like this, your legs can move a little bit like that, but I can't take my foot and put it like above my head, generally. And the other cool thing, you remember these constellation models that we talked about before? There's springs going and going everywhere. And that made actually like Rob Fergus's work in 03 computationally expensive. Here they said, you know what, let's be smart about this. Let's just make it efficient. And what they did is they made a star model. So basically this would be the root node, and basically it creates a star model like this, and computing this is computationally much more efficient. You need something called a distance transform, which I won't get into today. So basically then you had different parts put together by the star model, and the star model, again, so you have a root node with its leaves, and that allowed the deformations. The other thing was, you kind of allow these kind of local deformations like this that only get you so far. Imagine you have a bike like that one up there. You can imagine a bike up like this, a bike down like this. Maybe the wheels kind of move a little bit back and forth like this. But that only allows for a certain amount of deformations. If you have a bike that looks like, this one here, like a bike from the front, looks very different from the bike from the side. So they said, it was well, let's not try to fit them. Let's not try to cram these both into the same model. Let's just create two models. We'll create one, which is front-facing bike, and another one, which is side-facing bike. We'll train completely different models for both, and we'll recognize them both as bikes. So that worked pretty well. So this is the deformable parts model, the DPM. So if anybody talks about pre-deep learning phase, and they say, okay, what is the best model that existed before deep learning? People are going to say DPM, or the deformable parts model. And this is the model that I just described. And it had multiple components, again, to handle, is it a front-on bike or a side-facing bike? Had deformable parts, again, to allow for those deformations. Again, they used really good hard negative mining, and there's a good balance of all these different things. So this worked pretty well, but it still failed. Why did it fail? So I'm going to run through this pretty quick, but we ran a study where we asked humans to look at small little image patches, and we said, when you look at this small little image patch, what do you see in it? In this one, what do you see? You see a head, right? Look at that image patch, what do you see? Leg. Look at that image patch, what do you see? Nothing. And you do it with black and white images, low resolution. You can see that's feet, that's head, that's, I don't know, who knows what that is. And you ask humans just to look at these little bitty patches and to say, what do you see when you look at these little bitty patches? And we did that for this image here. And this is what the humans responded. So you can see the figure up there. So this is where people thought there was a head. This is where people thought there was a hand, an arm, feet. This is really good, right? You took this data here and you put it into the rest of the deformable parts model, you get really good detections. Like if you use humans as your low-level feature detector, this one and this one, even with gray images, humans did a fantastic job. You look at the deformable parts model, which had the same type of features, one for the head, one for the arms, one for the feet. You got a result that looked like this. You can barely even tell what's going on. Basically, you got the head right, and the post, and that's it. Here's another example. But this one's interesting because you have the horse, and people thought the feet of the horse were actually feet of the people, or legs of the people. But then you can see where the actual person was. They got the entire person. So you'd be able to say that this is a false positive here. Again, humans with black and white do a pretty good job. The machine totally failed. And what we learned from this was that one of the reasons the deformable parts model worked so well in humans was actually just it really did a good job of detecting the head. The other parts of the body were a little bit more fuzzy. But the underlying features that the SVM classifier was relying on were pretty poor compared to what humans can do. So if you looked at the pipeline, you had an image, histogram avoiding gradients, followed by the SVM classifier. We had these low-level features here. We had a limited capacity classifier, which is the SVM. What we really need is something new right here. We need better low-level features. And at this point, we're just like, I don't know. It's 2011 at this point. We didn't know what to do. So 25 years of feature designing, all of this work, and this is what we had. I'm friends with Peter, so I can make fun of his work. But you know, these are all the pedestrian detections on the side of the building. Yeah, I got a couple of them. That's pretty good. Maybe missed that. But we're still like I was at Microsoft Research at the time, and you know, a product group would come up to me and be like, Larry, I have this awesome idea. All I need is a cat and dog detector. And then I would just say to them, I'm sorry, it doesn't work yet. But I read this paper. It showed really good results. I'm like, yeah, ignore it. Like, it doesn't work in the real world. All right. We have 3 minutes left. So we're up to 2011 right now. And you might think to yourself, this is kind of depressing. It must have been a very depressing time to be a computer vision researcher. And don't take it as that. It was actually really fun, because there was so much uncertainty, so much more to be discovered. And there was something else at this time, which was kind of surprising. Anybody know Connect? Yeah, it's Connect. Do people use this anymore? You've heard of it at least, right? And you think about it. This is the age that we were in. And suddenly there was this device, this crazy device, that was able to do pose tracking. Remember we were talking about how hard it was to detect people? And this actually worked. I mean, at the time, I was just like, wow, I can't believe this thing freaking works. And given all the information I just told you about, and put yourself back in that time, you'd be surprised, like, how could something like this work given the state of the technology? Does anybody know the punchline of why this actually worked? What's that? They used random forest. If I would have taken that deformable parts model and I were to replace the SVM classifier with a random forest, it would have just not, it wouldn't have worked either. Depth. Depth is what made this work. And why was depth so important? Let's look at a depth image. That's a depth image. Is this easier to detect the human? Yeah. I mean, versus an RGB, color image, this is like night and day. And you take a random forest classifier, which you mentioned, and you say, is this pixel here closer than this pixel here, and then this pixel here, and this pixel here, and this pixel here, and this pixel here? You can say, well, I think that's kind of like a thing that sticks out. It's probably a hand. And it worked, because the input coming into it was so much simpler. And what I loved about this was it's saying, it basically flipped the research field on its head, because it said, I'm going to take these algorithms. We know we don't work on RGB. All the academics are just like focused on RGB because that's what's cool. And we're going to take something totally different, a different modality, depth, and we're going to apply it, and bam, it worked. And we got results that looked like this. So this is something that's interesting. When you think about yourself as a researcher, is the field is always focused over here. And over here, generally, is not where the big win is. A lot of times, the big win is over here. Always take a wide view. Otherwise, you're going to miss what's over there as well. All right, so in 2011, what worked? Face detection, characters, pedestrians, pose when you have depth. Did anything else work? Panorama stitching? CDs? That's about it. 40 years of work. Tomorrow, we'll learn about the rest. Thank you.